Continuing on in representing in what we do with graphs, we'll look at how do we represent graphs. Drawing little circles with little arrows is all very well and good, but it doesn't go directly to code. So let's look at what we need to do to represent graphs. First off, we have two approaches. Surprise. Would you like to guess what they might be? Well, we can use an array, and if we use an array to capture a graph, we call it an adjacency matrix, or we can use a link structure. And if we used a link structure to represent a graph, we call it an adjacency list. Here's a simple graph. As you recall, the circles are vertices, the lines are edges. The edges show relationship between the vertices. So we'll just use this little graph for the rest of today. So here's what we can do with an adjacency matrix. We put in a 1 for an edge, and a 0 for no edge. We could use true and false instead, but we'll stick with 1s and 0s for the moment. It doesn't really matter. This graph is bidirectional. We have bidirectional edges, so we put in a 1 for from A to B, and we put in a 1 for B to A. So the way I'd normally read across this is I would pick a row. We see I have a row for A, and then as I read across that row, I put a 1 in wherever I have a relationship, wherever I have an edge with another node. So from A, I have an edge to B, and from A, I have an edge to C, and from A, I have an edge to D. Now, you'll notice that these are bidirectional, so I'll have a corresponding 1 to indicate the edge going the other way. So if I read down the column labeled A, I'll see that I have a relationship to B and a relationship to C and a relationship to D. So A goes to B, B also goes to A goes to C, C also goes to A, and so forth. You'll notice the diagonal I've left blank. The diagonal shows a relationship from a vertex to itself. For instance, do I have an edge from A to A? Well, it's sort of an odd question, and you can get a variety of answers on it. But in general, we don't want to look at the diagonal. A lot of people fill the diagonal with zeros. Then again, a lot of people start with saying their entire array is zeros and then putting the 1s in where they have edges. So unless we have an explicit edge from ourselves to ourselves, we could leave it 1, or like I did here, we could have blanks. Doesn't really matter. We should never really be looking at it. You'll notice that we end up with a mirror image between the diagonal, above the diagonal and below the diagonal forms a mirror. That's because of our bidirectional links. Every place that we have a 1 from a vertex to a particular vertex, for instance, A to B, we have the reverse, B to A, and so we end up with a mirror image. Some people feel this way space, but it means that we can use the same representation for directional arrays. Also, lots of programming languages don't do very well with triangular matrices or ragged matrices. You can do them in Java, but it's a lot of extra work, and it really doesn't buy very much. So in general, we're just going to assume that for each vertice, we have a row that indicates its relation to every other vertice here. And that means that for each vertice, we have both a row and a column. You'll notice in this case, we have quite a few edges, and we have more 1s than 0s. This is not always the case. Here's the other option, an adjacency list. We take the same graph and we implement it. We create an array of vertex objects, and they can have whatever information I need about my vertex. Who knows what that might be? Certainly, at a minimum, it's a label. So we have a label. And then each vertex has a linked list of nodes, and the nodes identify the adjacent vertexes. So let's start with vertex A. So vertex A has a relationship to B, and it has a relationship to D, and it has a relationship to C. And so my linked list has a node for each of those relationships. And the order of these nodes doesn't matter, okay? As long as we don't lose it. So since A has 3 edges going out from it, its list will have 3 nodes. And the nodes will tell us which vertices they are. Now, notice what I'm doing here is I'm putting the index of the array in there. So for example, A has a relationship to D. The index that D is at is 3. So on my linked list coming out from A, I have a node with a 3 in it. That tells me I can take that 3 and use it as an index into the array and see that, oh, that's D. Then I can continue down the list, and my next node has a 1. I can use the 1 as an index into my array, and I see that that's B. Then I can continue down the list, and I can see that my next node has a 2. My 2 can be used as an index into the array, and that gives me C. And so we can see that A has a relationship to D, B, and C. The order doesn't really matter. We'll see that node vertex B has 2 edges, one to A and one to D, and it has the 2 nodes. C only has a relationship with A, and you can see it has 1 node, and that node has an index of 0. And if we look up at 0 in the array, sure enough, what's there is A. So the nodes on the list identify where the vertex is, not the name of the vertex. What we're trying to do here, so C goes to A, so C's list has the index of where the vertex A is at index 0. We don't want to store duplicated vertex information. It doesn't seem like a label is a lot of duplication, but that depends on what kind of labels we use, and it has some. And if we had other information about the vertex, we wouldn't want to store it in a lot of different places. And so this gives us a nice way of doing that. So the next obvious question, since we have 2 representations, is which representation should I use? Mostly it depends on sparseness versus fullness. The more sparse a graph is, the better using an adjacency list is. The more full it is, the better using an adjacency matrix is. If we look at the example of the simple graphs matrix, there are more 1s than there are 0s, which is very full. We're using almost all the space. There's not a lot of wasted space in it. This is not true of all graphs. We'll have an example. If we compare the street intersections in downtown Chattanooga to, say, the constellations on the star map, if you think about it, the street intersections downtown are pretty full. The streets pretty much all have at least one point where they cross each other. So each of the north-south streets crosses a whole series of east-west streets, for example. That's pretty full. On the other hand, if you think about a star map that shows stars, how many stars are there? Well, as Carl Sagan infinitely put it, billions and billions of them. Even if we don't go that far, we certainly have hundreds of millions of stars. And if we try to build a star map for all of them and we use a matrix, we're going to have very few 1s. We're going to have a lot of 0s. So if we use the constellation edges, the lines that make out a constellation, if we make those edges, let's think of something like the horoscope, the 12 constellations of the horoscope. Maybe there are about, oh, I don't know, let's call it a dozen or 2 dozen stars for each symbol, for each of the constellations. So we might use, maybe a couple hundred edges. Well, if we have billions and billions of stars and we have a couple hundred edges, we're going to, and we do it as a matrix, we're going to end up with a very big matrix that has almost all 0s and very few 1s. In that case, we're probably better off using an adjacency list technique. We'll end up with a lot less. So the break point of how sparse or full to switch, when should I switch? How full should it be for me to switch? It's really a matter of judgment, but we can always use either approach. In some cases, the matrix is going to get very full, and there is some overhead with the list that we avoid in the matrix. So if we have a mostly full graph, we're going to use less space actually using the matrix than the list. But we can use either one. And basically, which we pick has to do with this issue of sparseness versus fullness. Well, what if you're building something like a library and you don't know how full or how sparse it's going to be? Well, you either have to guess or you have to switch representations when it gets yay full, maybe some percentage full, something like that. In this course, it won't matter too much because I'll just let you know which one I want you to use. And I'm basically going to alternate because I want you to be familiar with both approaches. So let's talk about how we actually implement these. Well, if we're implementing a matrix, we need a two-dimensional array because each vertex is going to have a row and a column. And that could be an array of ints, that's what the book generally assumes, or it could be an array of booleans or an array of shorts or bytes. As long as we can get two symbols that we can distinguish from each other, we don't really care. That simply means that the edge is either there or it's not there, right? Implementing the list is a little bit more involved. Here are some sort of basic sorts of data declarations that you might use in a Java-like language. For instance, I have a class called Vertex, and it has a label, and I've made the label a string here. I could have other sorts of information with my vertex, but we're not really going to worry too much about that at the moment. And then I have a linked list going out from this vertex, so that's going to be to a node, and I call that head. So I have a list starting from head of type node. And then you see I have a class node, and it has an integer that I call index, and that's going to act as an index back into the array of vertex when I get that far. And it can be a linked list, so it has a next pointer. And then I declare an array of vertices of type vertex. So vertex vertices is some size of an array. You'll notice this is a one-dimensional array here, unlike the matrix approach where I'd have a two-dimensional array. This is a one-dimensional array. I'm simply holding all of my vertexes. Now, actually, if we had a really big graph, we might even use something other than a one-dimensional array here. I mean, maybe we'd use a red-black tree or something like that to make it easier to search. But for our purposes, we're not going to have more than a few hundred of these at most. And so it's just not a real problem to do a brute force search on a one-dimensional array looking at label. And so for our purposes, we're just going to assume that we can have a one-dimensional array of type vertex, and that when we need to find something that we'll just loop through from top to bottom of the array, comparing labels to the one we're looking for, and eventually we'll find it. When we find it, we can then follow its list along to get all of its edges. So that's all you really need to know for the moment about implementing arrays. A really nice thing is at this point you can go ahead and work on the next lab. You have everything you need to know.